All right. With that, we'll go ahead and get started. Thank you, everyone, for joining us back at Jetson AI Lab. Today is September 3rd, and we have progress and new work to show. Johnny's been very busy with porting the NeRF stack for neural reconstruction to Jetson, and we got that running and had been playing around with it, and it is really cool results that I think we'll be able to apply to like on robot scanning and different edge IoT devices. Also, I put out the OpenVLA tutorial last week. We'll dig into that and the results from it, and we're going with embodied agents and other models that have even come out since then. And also, we had release of Tau Toolkit 5.5, which has a bunch of new training recipes for transformers in them, and we use that as a discussion for getting into our own fine tuning and all of those workflows and everything. So with that, we're going to turn it over to Johnny, who's prepared a short presentation about the work that he's been doing to port the NeRF stack to Jetson. Thanks, Johnny.
Okay. Share screen. Can you hear me? All is okay?
Yes. Yeah, we can see you and hear you. Thank you so much.
Okay. Hello, everyone. I'm Johnny, computer vision PhD student at the University of Barcelona, and I'm going to present what I have been working during this last month. So I have prepared some slides. Okay, first, here's a summary to start. I would like to first thank Asir who brought ConfUI to the Jetson. I have also been able to bring the training process with a toolkit that you have seen in the LinkedIn post, and I have created boot dockers for easier use for the community. And well, what is new in the Jetson containers? I have integrated Mesh Lab, that is mesh editing and visualization. A cool map that is for 3D reconstruction for images, and these tools for summarize enhance the workflow for processing and refining 3D models that for example, I did in Computer Vision Master last year. So you can note that the documentation is still work in progress that I will do in the following weeks. And okay, let me introduce NeRF, that is the priority today. What is NeRF? So basically, NeRF is a neural radiance fields that is a technique that uses deep learning neural networks to generate 3D scenes from 2D images by learning a function mapping spatial coordinates to color and the density. So it has applications in 3D reconstruction, virtual essence generation, and computational photography. So with this application, with this NeRF, we have the spatial coordinates that you can see here. So we have the 5D dimension, and we have the spatial coordinates position and the viewing direction. Okay, so this is to feed into the neural network. So the output is a color RGB and the density of the sigma. And well, for each, so the color RGB and density sigma is doing for each point in a space, and finally the output rays are cast, okay, in through the sense. Okay, so the volume rendering accumulates the colors and densities along each array to generate the final pixel values seen by the camera. Okay, so for the loss is named the rendering loss, which is calculated by comparing the the render pixel values to the ground truth images. And you can see in the second row, okay, that made use a hashing technique to map voxel grid vertices, and another techniques like linear interpolation, concatenation, etc. So now let us move to the demos. Here is the principal demo today, that is run NeRF Studio. Okay. So if we go to the page, this is NeRF Studio that is called a lot of NeRF works. Okay, so we ported this for the Jetson, and well, we run the simple installation demo, that is these two codes. Okay, so we have to run the Docker. Okay, let me show in the okay, run that's the embed NeRF Studio. Okay, we are in the Jetson container, sorry, because it's not working the copy here. Okay, this is the first demo. The first time is, okay, this is the data set.
Do you know, Johnny, during the training phase, it takes all the images from your structure from motion set and trains the radiance field on them. At the inferencing time, does it regenerate an image or point cloud like every time you change the camera
after
viewpoint? Or?
Yeah, if you have the object, well, this during the training process, the inference will be fast. But today I don't have.
And I did mess with this last night and got it to all running. Him and I were going back and forth about it like all week. It would turn out to be like a 20+ gig container, all this. So it was very impressive. Thank you, Johnny.
Yeah. For me, it's very fast because, for example, it's a lot of train rays that you can see here. This is high. And well, it's only 1%, less than 1%.
Yeah, and when you first start this, everything looks blurry. Yeah, exactly. And like I'd followed NeRF stuff, but it recently has gotten to be quite impressive.
But in few seconds, it's like you can start to see that the objects.
I think it normally takes like about an hour
to do. This is a chair. You can see that. For example, a split screen, and you can see, for example, the depth and more options. Okay, this is the first demo. So during last day, was very crazy, and thanks to Dustin to help me, we import the first paper that is okay. 2 slides. That is a first paper that we implement with NeRF Studio, that is FruitNeRF. You can see that it's exactly that I explained before, but this model you can count the fruit that is in the tree. Okay, so you can construct the tree in 3D vision only with images. Okay, the paper is super nice, the examples. And you can do a clustering for different types of different moments of the fruit. So it's very, very nice. So here this model you can implement in a robot or maybe it's useful for agriculture with Jetson, etc. And what this is, what I will run the demo. Okay. First, I show you the dataset. FruitNeRF here. Datasets. For example, this one, no? You can see the all images that is in synthetic data. Okay. So all these images is useful for mapping the tree model. Okay. So we create a volume for this. FruitNeRF. Here is the data set. Okay. Go up. Okay. Maybe what is happening? FruitNeRF. Maybe it's this. Oh my God, what is happening? There are some it's a companion. Maybe it's the FruitNeRF.
I think you can just run this in the NeRF Studio container. I haven't seen it be specific.
That's the.
If you were to run all their like pre-processing stuff, then yeah, you would need NeRF container. But I haven't actually done all of those yet.
The image is well.
okay. Now you guys
the second day of the workday.
It's basically on par with the LLM side of things in terms of complexity, which like only reinforces that like there's this whole other world of folks out there that have been working on the like 3D graphics generation and reconstruction side. You can really see this become applicable to
this open a new world for Jetson.
I have a copy of this running too, if you want me to show it fully rendered after you walk us through it here.
Well, I think that is going fast, but if you want.
Yeah, or just change it to run in the NeRF Studio.
Yeah, because I don't have the.
But even if you were to, unless you have it pre-trained, everybody's just going to see the blurry one.
Okay. Perfect.
Okay, and then I can hand it back to you if you have more presentation to show here. Okay, let us see. Okay, I think this should be the one. All right, this was just running on my AGX from the same containers and Docker files that we'd been working on, Johnny. And this was not on the synthetic one. I ran this on their real data set. So it looks more noisy, perhaps. And it would seem like the rotation coordinates are reversed in this, but you can pan and like zoom around. And each of these is only of one tree out of like 3 trees in the row here. So the other ones do look more blurry. And Johnny, do you know how to get to show like the segmentation results in here? We're figuring all this out, and we'll make the Jetson AI tutorial from this. But
I didn't find in the FruitNeRF paper.
Okay.
Maybe it's a post processing after get the tree. I don't know.
Yeah, because the pre-processing. It's done in the pre-processing actually. Is when they do I think it's grounding Deno segmentation or SAM or one of the they pull in VITs that you installed in the Docker and then do segmentation on the images first, and then those point clouds then get fused in to the end results. But I'm not sure how to enable it in the GUI here, or if that's another visualization that they did. But okay, I can turn it back to you. But you can foresee this is essentially unoptimized from what we discussed and looked into the training and DNN backends that they use. If we were to speed this up or do mini versions of it, you could, in theory, use it for some type of real-time scanning or other object detection, point cloud processing, that kind of thing. It is cool being able to do this, and you can go and take your own pictures of your own environment and put them in there, just like you would another mosaic scanning thing. Okay, I'll turn it back to you, Johnny, if you have.
Yeah, no, if I'm finished. Okay.
Okay, and all of that is on. I meant to show all the containers that you've been working to put out. So there's now this graphics category, or there was enough that I added a new row here to this, and these ones that we talked about are on here. So as is, our normal MO with this group, first we start with doing the containers for these, and then we'll get more people to try it and do a little tutorial page on the Jetson AI Lab for this, and continue to build and explore other projects in this space. And there was a lot here that you ended up adding. So thank you. And a lot of these were quite tricky to get going. Yeah. So it's an interesting connection with the whole flux thing that you and Azir had been looking into, in combination with all of the simulation and synthetic data generation that
I think that people is working to create, for example, Flux output images and create a 3D model with NeRF, but it's still, people is still studying that.
Yeah, I think what I honed in on is when I was doing this tutorial for the OpenVLA, it was an issue of how to a normal individual build up all the sim assets for doing sim to real in a particular environment they have, like mine, outside of a normal warehouse or other thing that's already been modeled. And it would be really nice if you could just scan it either via a traditional SFM, or this seems even easier to use at the expense of computational power. So yeah, this run ran for 30,000 training steps. It took about an hour on AGXO, and I think the main thing is just the number of images and their resolution. Due to this being a real data set that was captured from an iPhone camera, I think it was. The images came in they were 4,000 by 3,000 pixels or something, and I had to reduce the downsampling that it was doing in order to get it to load it all. But do you know, does the amount of memory usage scale with the number of images in the data set, or
it depends of resolution, the number of images, because more images is more calculation, and depends of the output resolution also. Yeah.
Okay. I'm just trying to get a sense for how does this scale. Could you do it for much bigger scenes? Al, do you have a question there? Let's stop sharing here for a minute. We can talk. It looked like somebody had their hand up. But yeah, I know some. Okay, there you are, Al. Do you want to talk, man? We can't hear you. You're. See how quick his face changed. All right, he's debugging the. You're starting to come through.
Can you hear me now?
Yes. Yeah, we got.
Yes.
Okay. Well, too much technology. What was the batch size for the training per epoch, more or less?
Great question. 4096 rays, and I think I just set it to the normal amount of images because I was having trouble adjusting the training batch sizes with it. It was not taking them into effect, or it was still loading all of the data.
Yeah.
So before it actually starts the training, it does like the data loading. And I believe during that, it's actually doing a significant amount of pre-processing, camera calibration or alignment, things like that. And in that phase, it loads the entire data set, even if you told it to only use a subset for training. And during that, it was using an upwards of like 90 gigs of RAM on that little Fruit one until I dialed back the input image resolution to something like 1080p instead of 4K. And I'm unsure, like, how does that, because in the vision DNN world, we're certainly, okay, 384 is good. But in this, it might make a difference. I don't know. Has anybody else done these or have experience?
Yeah, the problem, Dustin, is that I have an AGX 64, you know that? And I've never been sure if the 64 is just for the GPU, so I can use it only for training,
both.
or
It's unified.
Both. It's unified because usually in computers you have the GPU memory and the RAM, and they don't talk to each other. But apparently in this they are kind of mixed. So
the problem is most training scripts are set up for that paradigm still, Al. So even though Jetson is unified, it's the same physical RAM, they might be maintaining two separate copies of the data because they don't realize that or aren't optimized for that unified memory architecture.
Because in the background, NeRF Studio use Tiny CUDA, that is a repository of NVIDIA that is the minimal functions to run NeRF Studio. So it's not prepared for the Jetson architecture and similar unified memories. So I think that it's there is a room for improvement.
Yes, I know that there is. And I believe like the interest of the FruitNeRF and all these others internally have started looking at this too for like actual integration with Isaac Sim and SGD and like the whole thing that we're envisioning here. So, and I know that the ultimate thing is just be able to tell the sim like, hey, generate a scenario with this, this, and this, and it goes off and like does that via techniques like this.
So I would think that since we're sharing RAM for the training and for all the stuff that the OS uses, that if you want to increase the batch size, then try to make sure that the OS uses as little RAM as possible so you can actually get to use it in the training.
Yeah.
Did I get it right? Pretty much?
Yeah, if we went in and had it use like CUDA malloc managed instead of ordinary CUDA malloc or do the CUDA memory copies and things like that, then it should significantly reduce the amount of RAM. It's just a lot of those training scripts, they're not set up for ARM devices, not to mention like a single little edge thing. They're more focused on multi-GPU, multi-instance to, great effect. And even so, I guess I'm more interested in how does it scale for gigapixel size data sets where it's way more than just one tree, or like I'm going to capture the whole orchard of apple trees. Can it be used for global mapping, or is it really only just like local mapping? In which case, the hour-long scan time is kind of problematic for real-time things, and we can look at optimizing that in the future. And I know, Al, you've been looking at like the more VR side of thing, and I think you said you've got the Meta Oculus Quest 2, was it? I think you got working?
Well, it's actually Oculus One. I got the demo ready here for whenever you have some time, and then.
Oh, you want to fire it up and show it to us? Go on. It's funny how we're getting more into like the VR side of things, a little bit like the graphics now that we've been doing sim and things. So if you wanted to talk about what you envision using that for, I don't know how it's connected with your smart trash bin or whatnot. Feel free to take the helm. minutes here.
The thing is, I have this robot here, arm. I don't know if you can see it. Okay, this is a Dobot version 1. Okay, this was when Dobot was starting. It was a Kickstart project, so it is very limited. It's not like those fancy Dobots that they have, Magician, etc. The protocol is iffy to just make it nice, and then, but nonetheless, my idea was to integrate it somehow with this, which is not the best either because this is not Oculus Quest 3. This is the Oculus Quest 1, which is again iffy. So it was challenging because both are not the best, but nonetheless, I was able to make it work. And I put it on this here thing, on this repo, which I will share right now here.
Nice.
Okay, I just
traditionally VR headsets are not super easy to get working on unsupported architectures or whatnot.
I spent 2 weeks messing with the Oculus SDK, and then I tried the SDK from Steam, and it turns out that this particular model is weird because even though you need a Steam connection thing, you can load it, but you cannot load it. And then there's this hackers that were able to create an APK that would use the Steam thing, but it didn't work. All of a sudden, I found this library developed by some university people, and it was so much easier because this library, what it does is that it loads automatically an APK in your Oculus. It fires. It creates a daemon so it can connect, and it does it automatically for you. All you have to do is to just follow the steps. And the only trick that I found is that these Oculus things keep going offline all the time, and then therefore they no longer send data, which is really annoying because you have to keep putting this thing back. But I found out that there's this software, and I put a screenshot at the repo, and then called SideQuest. I don't know if you know that software, but with SideQuest, you can indeed make this not stop working, so you can actually get working. Otherwise, you're working and the thing goes offline and the connection is lost and you have to start all over again. So with that in mind, let me try to, if that's okay.
Yeah, that's awesome. And it looks like the library is from the Berkeley Rail Lab, which is the one they make the OpenVLA and all the other ones. It makes sense.
So let me see. I don't know if you can see it.
Yes, we can see it. You're also a MOBA Xterm user like myself.
Yeah. Okay, let me see. Hold on. Make sure that. Okay, let's see if this works. Okay, see that heal and tail bytes are incorrect. This means that it was unable to get the original position of the robot. Like I said, this is the first version, and the protocol is not the best. So unless we get the original position, we don't have a demo. Let me try to ensure. Sometimes you know what it works. Just to unplug the serial port and plug it back in. Let's see if it works now. Okay, not receiving data. Put your heads on. See what I mean? Can you see that bunch of data showing up?
Yeah, yes, we can.
Okay, now I'll have to stop sharing so we can actually see my camera. And I'll let you. And I use these controllers here, and maybe make it work. Because like I said, the protocol, hold on, let me see if stopped receiving data. It's receiving data. And then the problem is this robot, its serial protocol is.
There's a lot of bits in the pipeline to get broken there, and I understand from looking into those in the past. It's tricky to get them.
Let's see, hold on. Give me a second. This doesn't work at first. And then
I do have a bunch of questions for you, but I don't want to distract you as you're.
Okay, now receiving data, put your heads on. Okay, now we're back. See? I don't know if you can see it.
No, I don't see what. Is it moving the robot arm?
No, it's turning. Can you hear the sound?
No.
It's turning on and off the pump.
Okay.
And also,
I hear something. Do you see does the displays work?
No, because there are two ways of the displays are transformation. I'm just using at this level just these ones here.
Okay, you just want it for the control.
Yeah, exactly.
Okay.
And then because it's much easier, the transformations they require 3D control and it's much more complicated.
So like teleop control, and you don't really need the camera because you literally are looking at the thing. And that's because
I just need the camera to keep this thing running because
it's still
even with that thing, it turns off. Hold on.
Okay. Have you gotten the camera to work before, or the on-screen displays, or is that not possible?
I'm working on it. Give me a second.
Okay.
The display is more complicated because I plan to integrate. Okay. Can you see the robot moving?
Yeah. Okay. All right.
Doing something. And you see that I control it using this.
Okay. I assume that you've had it where it does actually follow what you're. How precise is it in your experience?
The robot is really precise. It's just that the connectivity is really bad because of the unbelievably crappy protocol this particular model uses. As soon as they started to sell, they just moved into another totally different. This is only 9600 BPS. I mean, that's very slow. Then they moved to 115, and then which of course is much faster.
Okay.
So yeah.
Well, unfortunately, the more gating item is on the VR headset side, who traditionally do not have open access, like you mentioned that APK. Oh, okay. It looked like it was just laggy.
Yeah, it was. Like I said, it lags because it keeps the data in the FIFO, and then all of a sudden it decides to move, and then stops again, and then gets more data because it's so damn slow, the connectivity. So yeah. So,
but that's solvable problem. It's not as if you can't interface to it at all.
If you get proper hardware, it should work like a charm.
Yeah.
That means a real robot with a real connectivity and a better Oculus Quest, because this is the version 1, which is, I think that they only produced for 6 months and they quit because it's such a piece of garbage.
Yeah. Well, obviously that's a trade-off of what we're all getting into here, is that some of this hardware is actually considerably expensive, especially on the manipulator side, and it's a very active area of research and development. The advanced teleop rigs and stuff, and some of these go for $50K plus for these. So to be able to start doing it on just commodity consumer hardware, even if it's a generation old or whatnot, it's great. Hey, Nigel, you there, man? You have a question?
Yeah, just love this. I'm doing something very similar right now, and I just want to confirm, is all of this VR binding being done on Jetson, so ARM64 iGPU? Yeah,
this is connected to an AGX. don't know if you can see it here.
I
My
trust
little
you.
baby.
Yeah, take a look that he dropped in the chat, Nigel. It's
Yeah.
a library from Berkeley that just like
Very cool.
Yeah.
does it. Yeah.
Yeah, that's
What I did was use multiprocessing because the library actually uses multi-threading, and I noticed, at least in my lab, that multi-threading does not really do the work. You gotta do more, go for the full-blown multiprocessing,
in Python.
and then and this is very cool. This is really cool because I thought I created. If you look at the code, you will see that it's actually 2 modules. Okay, and both do run forever, and both share a single variable that is read for as many modules as you can ask. So if you need to ask create another module, feel free, just create another module and bind it to that library, and then you can add as many variables to that library as you want, and each module is always on a constant loop. So basically, all you have to do is alter each one of the variables that you need, and because all these modules are always reading those variables, as soon as they understand, okay, the variable has changed, they do something. At the end, they reset the variable and they keep on doing. Has the variable
changed? There's a trade-off in the overhead, Al, where sometimes it is better to be a multi-thread, or is it passing video data, latency sensitivity? The problem is the Python GIL interpreter lock, which there are groups working to remove, and making faster progress on that actually than anticipated. But
at one point,
there's also overhead from like loading CUDA context libraries multiple times and such. But in general, yes, you are correct, especially if you have like real-time stuff that you want segmented off, or like the NIMS inferencing microservice architecture, stuff like that. For folks that are doing real-time embedded systems, it makes sense to, consider what you want in each process. And also with Ross is very nice at handling all of that for you internally. So there's like a happy medium as to you don't want it for like literally every last thing. Like in those things in the Agent Studio design, like sometimes you want multiple of them clustered together in a process. But yes, unfortunately, I've seen it too in our most complex agents that have like, 30, 40 different threads running. The GIL lock actually does come into play, and you can tell because it's kind of like your robot there where like times out and all of a sudden catches up real quick. It's because that thread wasn't getting run. Meanwhile, most of the CPU is idle. It's because of the GIL lock, and the sooner that we can get rid of that, the better. And there are a lot of folks for actual deployment, like, okay, we're just going to go back and port it all to C++, which is like what our traditional background is from embedded systems, of course. But the scale of the stacks these days and the speed at which it moves, it just seems impractical to go off and re-implement a lot or all of that in totally different environment and still be able to keep pace with things. I know on like LLM side, at least, they have specific parts of the inferencing pipeline in place. But once you start adding on all the other like RAG and all the other techniques that are on top, function calling, grammars, everything else that goes along with it, and all the other plugins and everything, it just becomes kind of impractical. But yeah, I totally hear you. One issue, like I mentioned on the smaller Jetsons, like over Nano in particular, if you have multiple processes, then sometimes it can be loading the libraries multiple times too, which on x86, they don't care because they have servers with like hundreds of gigs of CPU memory that they don't mind if you're loading PyTorch 5 times. but it does make a difference for us. But thank you very much for digging into it. It is going to be quite frustrating. If you keep on it or make other progress, let us know, because I would end up using that in the future as we get more into like this interesting melding between 3D generative graphics, VR, AR, and like sim to real robotics. It's kind of like all coming together here in a very interesting way.
I can tell you, I started with a Jetson Nano, and that thing was a nightmare because of power problems, etc. And then don't get me started. Still, I was able to get stuff done, and then I moved into a Xavier. I didn't have power problems anymore, but I had all kind of not being fast enough. Now I have an AGX, and now I'm getting stuff done. The problem in this market is that you depend so much on hardware that at the end you need to open up your wallet and buy the latest hardware. Otherwise, you can be the best coder in the world. The hardware does not help you. You are unable to get stuff done. So yeah.
Yeah, I will. Let me jump in on that from a having run companies that use these NVIDIA embedded Jetson systems. While maybe our end customers get excited when they hear about a new a new module, a new chip, it's a nightmare for companies, right? Because it's the amount of work to bring up and integrate, not only the software, the hardware, and everything. It's two-sided sword, I guess, right? Obviously, from the research developer, the next generation, that's great. You're going to get that much more done. But there's nothing worse than having a customer say, "Hey, call me back when you're on the Orin or whatever," right?
Yeah, no, I feel you. And with all the jetpack combinations, and like a lot of us are in the same boat. We support a large community of developers just like us, and there's like a growing number of Jetson variants out there. I think Orin has at least 6 or 7. It got to the point where like I've lost count. I used to be great with like rattling off the speeds and feeds of like every GPU, and like I can't do it anymore because there's too many of them and all the jetpack combos. But at least a lot of the software support has been like merged and streamlined, so it's not quite as big of a difference. But in embedded systems, where like we're doing the physical integration, and sometimes you can't get away from the fact that there's actually like people have to go out and design the actual physical enclosure for that system and its cooling profile and power and all of that, even though it might be the same form factor. And Al, to your point about like the barrier to entry of cost of this, as we try to continue to drive it down, and from our end, make things available like the educational discounts, and always want it to be possible for anybody to pick up. The reality is that it's still, the prices comes down over time, but there still is a barrier of entry of, if you can't have at least like a few $1,000, it seems, to, get the compute, get some rudimentary robot arms, some cameras, your VR headset, that would seem to be the entry point, unfortunately, which is way lower than like, hey, I need like a startup with hundreds of K of funding or whatnot, which is, as part of this group, what we're trying to kind of emulate is like, hey, there's all these cool Y Combinator companies or whoever out there doing embodied agents and having lots of compute funding for them. How do we do that just as like individual guys, and come together and see what we can do? So yes, unfortunately, you still do have to have some stuff. And that's why with the OpenVLA, I did it in sim first so that nobody would need to go out and get all those parts. And we can segue into a quick discussion on that and the results, since it interestingly ties all back in to the graphics and VR and that stuff. Let's see, what tab was this in? Okay, so we had been talking about this in the meetings for a few weeks as I started to play around with it, and published it, I think it was last Monday, that I put it out, and comes with this demo in the Agent Studio of it picking and put out the pre-trained model and like data set for doing this. It was not easy getting it to be dexterous enough. That's why I think in future plans for this, I'd like to dial back the complexity and degrees of freedom. Something easier like an AMR or ground robot. I think it might be a little bit more palatable for the likes of us to get into. Paul, you had a question there.
Yeah, you were taking me off the screen again. Your OpenVLA 7B plus stack, where's that come from?
That's a great question. So the VLA is essentially just the vision language model, and in this case,
7B.
it's Llama 7B plus Dino V2 plus Siglip. So it was just the same like live lava stack that's in NanoLLM, like the same one that runs this, just with like a little different thing at the end. I'm sorry?
How do you get it into the studio?
Oh, I have a presets in here that you right click and do it, and there's also a code example down here of you can use it directly from your Python script if you desire, because a lot of this would be integrated into like a ROS node or a lower level robot in there, but it's all built on the same exact LLM, VLM. This is using MLC for the quantized inference, and it turns out that was like the easy part of this study. That was I think I presented these kind of results 2 weeks in. I'd had it running in our whole, streaming vision language model runtime at the edge, and got considerable, almost 3x perf improvement from it. Then all started in on like the validation to test that this was actually all working, and that's when it got way more complex, because it wasn't as if in this section I discussed this, that hey, just confirming this checks out via the test data set is not indicative of it being successful, because you can confirm that frame to frame that hey, the accuracy is 95% what the original data set said it was, but it's not dynamic, and all those errors can like add up in non-deterministic ways over time. So you need an actual online environment to evaluate, is it actually successful or not at each task, which is like the ultimate metric that's presented at the end of the paper. And unfortunately, in the real world scenarios, they have a very limited number of these trials they can do, because it's so physically intensive and time consuming to do that. And more folks are now using these simulators to do it. And again, it's not just any simulator, it's a simulator that needs to be able to generate endless labeled training data with the natural language
You're muted. Or the sudden somehow.
I cannot hear.
Sorry, I muted myself. Am I back?
Okay.
I was trying to.
Okay,
I think I was trying to.
You're back. You're back.
Thanks, guys. So yeah, the Mimic Gen is made by the Groot team, who has been working on embodied model for humanoids, and basically this takes in 10 teleop episodes and then just generates an endless stream of synthetic data based on that. So it's essentially it's able to say, well, in the teleop version, you connected block A to block B, and then it's able to interpolate those states from the sim as long as you don't really change the fundamental topology of the scene, if you go on to add in other objects or wanted to manipulate other things in the trajectories, you would have to get new teleop data for that. And then essentially we train a fine-tuned model on that. I've done like dozens of these to get it all going and like the hyperparameters tuned. And it was a very interesting study of the different options out there and how accessible is this for normal folk. And it turns out like it is not too bad spinning up one of these spot instances to do it, as long as you got the data in your training pipeline figured out. Here's a bunch of like the training results from that. And then I done a bunch of LoRa's on the Jetson itself before doing the full fine tuning in the spot instances. It turned out that this sim environment was significantly different from just like their base data set, which I think we'll see that more going forward. And then that led us to be able to do like the final validation on it with actually measuring the task success ratios. And we can see that it able to achieve an order of 85% success on this very simple block stacking task. I say simple, in the realm of like dexterous manipulation, it's gotten quite advanced what the state of the art can do. In my personal scenarios, even this block stacking is a little more advanced than just some like basic things around the house here, whatnot that I wanted to do. So this would be good enough. It's more about like reducing the complexity of the workflow, computational requirements, getting like the mini VLA version of this, as opposed to one that's based on the 7B model would be nice. So it could be much faster. It's basically too slow to use still, because it's running at like 3 FPS. And that it was also an interesting part of this study is how that real-time feedback loop impacts the performance and accuracy of the system, because the faster it runs, the faster it can make these smaller corrections. And there's other things we can do, like train it for larger time steps. And yeah, I'm going to try it on UGV and have one of these that I've been working to upgrade to Orin, and had one of these for like a few years, and just been waiting for these cool Gen AI models to roll around that are more intuitive to learn and do the training on. And Al, like you've been working on with the VR, I think you can like connect this thing with teleop and like the FruitNeRF and like the whole thing, and could make a really interesting workflow out of that. As we are all getting more into training, fortunately, the Tau toolkit has been adding more support for fine tuning of these different VITs, and in the future, you know, getting more into VLMs and VLAs. And it will be important that everybody's able to go off and fine tune these models themselves, get their intuitive data collection workflows down. And we released this Tau Toolkit 5.5 update. So I encourage everybody to go and poke around the documentation for this, learn what it's like to like submit the different commands or what data set formats that you need, scope what type of systems that you'll need for it to be scalable, which really this whole study here was, it wasn't so much just, oh yeah, we got the robotic arm to stack blocks in a simulated environment and took like all this compute in order to do that. It was really to characterize the workflow and scalability of it. Like, how long does it take? How easy is it? How much does it cost in compute? Or how long per task that you want to train it on? So understanding all of those things was incredibly valuable. Basically, it all comes down to these two tables here at the end, which is like, based on how many fresh episodes of data I gave it, here's the overall success ratio. So yes, it did take a lot more episodes of it in this case. I'm not sure if that was just because it was significantly different environment or what. I did notice in the training results here, there's an interesting hidden one that shows the difference between just using OpenVLA from scratch or with the pre-trained rates, pre-trained weights. Sorry. Okay. So let this refresh here for a sec. So this one here in the orange is if I just started from the prismatic VLM base. So if there was, it's as if there was no VLA training at all. And then this one is like with the normal OpenVLA, like I trained on top of OpenVLA. And the difference was only 6,000 steps versus like starting entirely from scratch and throwing the weights out. So it's kind of TBD to what extent this is like foundational model per se. The work hugely impactful, and that's, I believe, reflected in the amount of interest in it and the number of views, and also of all the other ones like this Crossformer that came out. I think I have some of these here at the bottom that I list. Crossformer and this embodied COT. So these are coming out like every week now practically. It's impossible to keep up with, so you got to pick and choose real wisely. But this one in particular was derived directly from OpenVLA, but did not use the OpenVLA weights. It started from the VLM base weights. So, and this whole discussion in this study here of overfitting and how much of that is done. So it's like, is it actually foundational model and generalist at all, or are they off by an order of magnitude on how much training data is needed to achieve that? Al, did you have another question? Your hand like went back up.
From what I can gather, OpenVLA seems to be a mix of a database of pre-trained movements like pick up carrot and drop here, plus a generalistic model which is able to translate vision into movement. Did I get it right?
Yeah, well, and the natural language component is important.
Oh, yeah.
So there are many others, and like the diffusion policies we're looking more into as well, and those are popular as too, and faster. They can be faster. So if you don't need such natural language integration, you can look towards, and I know Nigel's been looking at like Aloha and others. There are ones of those that, in theory, you could make an age noun of with a function calling LLM that will then call your different policies that do not have natural language support in them. This one is an interesting melding that does, this is, I would not call this an LLM, but it is like outputting tokens, like a Florence-like VIT. It seems to be causal. It's just not an LLM per se, and it is doing this cross embodiment thing where it has these different heads that are trained for different robots. Each of these actions can be of a different degree of freedom. So it is interesting architectures these popping up. I still don't necessarily feel that any of them are foundational or, you know, generalist, like, hey, I can just drop this robot in and not really need any fine tuning on it. It seems to always be so because they all use overfitting to achieve the success ratios needed to, you know, these tasks are highly complex. And that is kind of what I want to look at next, which is, hey, if we go from this like 7 degree of freedom manipulation space, that even though, yes, the block stacking is supposed to be like the easiest one, in order for it to achieve that over, you know, 100 plus frames, is actually a considerably complex task for us in computer vision here, especially considering like, hey, it can't let go of that gripper one time or mess up one time and the entire episode is ruined, which is the whole reason we needed to evaluate it from a task success standpoint in the first place, as opposed to the accuracy. And also, like, the average number of frames it takes is also important, because if it takes way longer, that means it's slow and inefficient and like bopping around. And like automation guys, they want it to be as quick and zippy as possible. And to put in perspective, this should be around like 110. That was what the human teleop achieved. Most of these episodes average at 110 frames. So it adds an extra 20, the VLA does. So, but it's not optimized for. Is something that it needs to be trained. But okay.
Dustin, can you put back the cross-former page?
Yeah. I'll put that in.
I was typing it and I got it wrong.
Okay, sorry. So, yeah, and it's here on the Jetson AI Lab page as well. Now let me. Fine. Here it is. Cross-former, and like every week.
Model GitHub.io. Okay, that's what I got wrong.
I'll put both these links in here.
Okay.
This one just came out last week, I believe, and every week Berkeley's coming out with like amazing stuff, and other research groups too, but them in particular just seem to like really be taken off. And we've been fortunate, some of our interns over here from the summer like work with them, or hell from that university or others working in this space. So I think at this point, as opposed to being tied to any individual thing, like this is not like Llama, our savior, is going to like put all your eggs in one basket. I think it's more advisable to kind of really dig into this, learn the ins and outs, try the VLA architectures, try the other VIT based ones or the diffusion based ones, which we'll get into more, because like Johnny, Azir, what they've been working on, like the diffusion side kind of brings all of this together, not only from like the sim perspective, but also like actual inferencing is using diffusion models too. And people like get their own pipeline for this. You have a higher level agent that just kind of like takes in everything, not only the image from the camera, but like the previous state, everything going on in the world space for the robot, and then outputting its actions or text to communicate with the user, like the whole agent wrapped up in one. And a lot of these frameworks like Hugging Face, LayRobot, or what Berkeley has done, or other ones, people putting their own models in there, is so you can much more easily just go in and tweak it for your own needs and be able to adapt it for your own inputs and outputs and tasks and things like that. So it would seem that on this scale, fine-tuning these is not some insurmountable hurdle. It's something we're all going to have to get more comfortable with as our applications get more specialized. It's all getting very real pretty quick here, all coming together, and it's been a great summer collaborating with you guys at this group since GTC when we initially met. If you look back on like our pre-recorded episodes, we've come up far way. You're just like grinding it out week by week here, and you can see these trends where the directions that we're heading with things, it actually is starting to transition to like getting out there with like the real robots. And I intend to use this for just like basic tasks around here. I want a robot that can go around and haul around firewood or like whatever easy stuff that is just like the priority order of like mowing the grass takes up the most time, right? So just like keeping things simple, and from a practical standpoint, like what are your own personal things that you need automated in your life or can stand to improve the efficiency of, and continue diving into that and driving it to, bring those AI models to bear on some real world use cases, I think is great for everybody to do. So with that, we can wrap up soon for today. If anybody else has any other questions or discussion topics they'd like to chat about, feel free. But barring that, we'll meet again in another 2 weeks on the 17th of September. In the meantime, I plan to continue messing with the VLA and the VLM and these other diffusion models and get them working on ground robot and start to integrate back in with like our existing ROS stack and the NAV2 system and get it so that these are actually usable. So being able to tell the robot, hey, go to waypoint XYZ, and it like drives there and comes back or follows you and basic things like that. And over time, ramping the complexity back up to include manipulation again, I feel would be good. Or just like basic stuff. Like that manipulator arm I showed you on my outdoor robot. I just want to like put like a drone motor on the end and have it go around and like weed stuff or like pick cherry tomatoes off the vine or like very basic stuff. I feel like by proving the block stacking, that is actually more dexterous than most of the things that I want to do around here with it, which is fortunate. Others that are working in the research space in like kitchen environments or factory line assembly, like they're working on very high-end solutions that are approach like human level of dexterity on things. And obviously that would be nice to do someday, but for now we can just keep it simple on that. And it'll be really interesting to see how merging the autonomous ground navigation stack with the mobile arm base works out in outdoor environments, because everybody's been indoors in a kitchen or warehouse essentially to date. So yeah, that's like kind of the path that I'm going down. I hope everybody out there has something that they're passionate about or foresee the use of this. It seems like for 10, 15 years now, we've been gearing up this stuff to be used, and lo and behold, day is finally here where we can just roll it out and start to use it in the real world. And I think a lot of that is because of like the intuitive nature of the natural language prompting. But that's not to say everything actually needs that level of it. Like with some of the UGV models out there, they don't need such extensive natural language prompts. You don't always need a full Llama 7B or larger for you just to tell it to, go to the next waypoint or stop, or it's much more limited natural language commands. The reasoning based on the visual inputs from the VLM is actually much more significant, I feel, than just responding to users' query about it. But yeah, we need to get them more optimized, get more training and data in there. Having other people go and explore it more would be great. And overall, figuring out this huge, massive workflow of like, hey, I've got my robot, I scan the environment, have my neural reconstruction field for it, have it in Isaac Sim doing SGD, training the VLA or the diffusion model, back out into the real world, collecting all of like the data and getting that workflow going to teach it new tasks. And then we will know like how long does it take to teach it to do something new, which I feel is like the big thing that we're trying to figure out and characterize for all of this. So as always, thank you guys so much for the interactive session. Al, thanks for showing us the Oculus thing. And Johnny, truly appreciate it. The past week or so, you've really been putting a lot of extra time to get all of those containers working and to get us all started on NeRFs. And that's not to say like, we're not going to use like the NeRF Studio for runtime inferencing, but it's not dissimilar to like when Shakizak got us started with Llama Factory, and then we started doing our own fine tunings, and lo and behold, a month or two later, now we're doing like OpenVLA on Cloud Spot instances on 8 H100s and stuff. So like you can see, like we will get into it more over time here shortly. But yeah, stay in touch, you guys. If anything comes up, feel free to ping me or get in touch. As always, love these meetings. Thanks everybody for sitting in. We'll see you again on September 17th. And yeah, thanks and have a great afternoon, everybody. Take care.